Welcome to SoilStructure software. This is a demonstration of version 3 of cantilever retaining wall / restrained retaining wall, which was released in July of 2016. In this example, it's example 1. It happens to have 3 stem sections. So the way the software window is arranged is that in this column, the left column, we have inputs. The middle column, we have results. And the third right column, we have diagrams. This is the construction. You can click on it to view, and it will show you what the dimensions are, what the height of the stem is, the width of the footing, the keyway depth, and it will give you the bearing pressures for the toe and for the heel. You can also look at the reinforcement, and if you click on it, you can view and see the upper stem connection to the middle stem, which is also connected to the bottom stem, how the heel bars are developed into the toe, and how the toe bars are developed into the right, and how you have the keyway reinforcement. So with that, we have, as we said, 3 stems, and we have the unit weight, 60 KSI steel, half a foot parapet height. And if you look at the construction, you could see that this is the half a foot parapet. It's measured from the top of the stem. The codes used, we're still using 2012 and 2015. The retaining wall sections are nearly identical, but we did switch to ACI 31814. The backfill soils, in this example, we're using equivalent fluid pressure. You also have option to use Rankine method, where you enter the friction angle and the unit weight. We have a Coulomb method, which has wall friction for the active and the passive condition. And we have a new method called Mueller-Breslau, and most of you are familiar with his work in influence lines. But he also took the Coulomb equations, and he added a modification if you had the backfill wall. So, for example, the back wall of the, let's zoom in here. If this wall is vertical, you can use Rankine method, you can use Coulomb method, and you can use equivalent fluid pressure. But when you start to have an inclined wall, where it's inclined into the hill or it's inclined away, so that means it's no longer 90 degrees, it's either less than 90 or greater than 90, then we cannot use Coulomb for that. He doesn't have a solution. But Mueller-Breslau did that. And so in this example, we're using equivalent fluid pressure, but just be aware of that. So we used active of 40 PSF per foot, which is same as PCF. We used equivalent fluid pressure of 250. The backfill slope is 18.4, and if you click on it, you could see it's 18.4, which is 3 to 1 slope. Soil cohesion 150. This 150, which is in the backfill case, in the backfill soils, is only used for global stability. If you wanted to know what's the maximum vertical cut you can have. We don't use that to reduce the active soil pressure. Soil or rock unit weight, in this case, is 110. All of this will be coming from your soils report. Allowable bearing capacity happens to be 2500 PSF. We have 3 different methods of entering the seismic load-in. One is the seismic KH, and you can use the 2013 Nicola / CTAR method, which says, so if we were to go into the stem section and look at the stem forces, what that says is, well, this blue line is the static earth pressure, and as you could see, the red line is your seismic earth pressure, and you could see here, you can put it there, and then you'll see at the bottom here what the number is. So soil pressure at 12 feet for seismic is 189.75 PSF. This is based on research by Nicola and CTAR. So let's close that. Another option will be to use inverted triangle. Now in the code, it doesn't say whether the seismic earth pressure should be inverted triangle or not. But if the reviewer insisted on it, you can enter that as inverted triangle, go back into view stem forces, and now you could see the red is inverted triangle. So it's inverted triangle. This is the static earth pressure. This inverted is the seismic earth pressure. And the green one is the strength load combinations. You add them two, and then you use the load combination 1.2D plus 1.6L plus 1.0 earthquake load. We also have another method of calling the uniform seismic pressure. So if you have a soils report that says, for example, you have 15 psf rectangular distribution for seismic earth pressure. So you would go into stem and you'll say view stem forces, and now the red is rectangular, the triangular blue is the static, and then when you add the load combination, that's the green one. This will be your shear, this will be your moment envelope. The envelopes are red, and then this is the actual, and then this is the deflection. This is version 3, we introduced the deflection. So let's go back and stay at the 2013 Nicola. Okay, so next we go into passive soils. The sliding friction coefficient happened to be 0.33. Passive slope angle is level, so that means this slope in front of the toe is level. Soil cohesion from the soils report is 150 in this example, PSF per PSF. It doesn't, by the way, have to be the same as the backfill. So you could have a different soil in the backfill where cohesion may be 300, and you go down to passive soil and you may get 150. Ignore passive height. You could have it 0, or you could have it a foot or half a foot. It's up to what's in the soils report. Now we'll give you guidance. So if you click on this question mark, it will give you that consistency of cohesive soils per USCS classification. And these are the values we suggest: 100, 300, 600, and so on. Global stability of a vertical cut. This is really ideal for somebody with a more geotechnical background. So if we click on it, and you need the wall friction angle. So if we said that the wall friction angle, in this case, for example, it's cohesive soil, let's say plastic silt with some clay, was 22 degrees, then what you do is you go to the global stability, and you can see red. What that means is the program is saying that you can cut vertically up 6.47 feet, and then you have to slope it the remaining height at 1.5 horizontal to 1 vertical. Most people say 1 to 1, but that's too steep for a 22 degree soil. So that's why it's failing. So you may design everything to work out for a 12-foot cut, but plus the footing, which is 1.33, but when you make the excavation, you can only allowable excavation height is 6.47 feet. If you wanted to do shoring, that's another option that you have, that you can do shoring. But if shoring is not in the budget, then you'll go up 6.47 feet, and then you'll lay back the remaining 6.86 feet at 1.5 to 1. So that's why we use that. So let's take that out and go to stem section design. So remember we said in the general data we had 3 stems. So usually we start with the bottom stem. You can choose if it's concrete or masonry. You can put your F'(C) or F'(M), depending on if it's CMU or concrete. You'll put the wall height. Now in your demo it's fixed at 4 feet, all the stem sections. That's the only limitation we have. But you can change the rebar, you can change the stem width, you can print it and everything like that. So we have in this case vertical reinforcement is number 5 at 8, and it's a 3-inch cover. So if you go here under reinforcement and you blow that up, you could see that the vertical is number 5 at 8 with 3-inch cover and horizontal. Let's say I wanted double reinforcement. We can do that. So if we say we have double curtains of steel, and let's say on the other side it's not as important, I just wanted number 4 at 18, and then obviously you'll need the horizontal bars to hold them up, and then you could say I want number 4 at 12. Let's leave it at that. Now we go back and we click, and you could see that it's number 5 at 8, that did not change, but on the exposed face we have number 4 at 18 and number 4 at 12. You could do the same with all 3 stem sections. So let's take that out, and let's take that one out. Go back to construction. Okay, so the next one is, by the way, before we go through that, you can do the same thing with the middle section. you have it masonry in this example, and then in the top section we also had masonry, but the width is changing. So the upper stem is 10-inch masonry, the middle stem is 12-inch CMU, and the bottom stem is 16-inch RC. Next we go to footing dimensions, and we happen to choose 2.17 feet of heel and then 4.5 foot of toe, and we made the thickness 1.33 to meet the development length at the hook depth of number 5 bars coming from the stem. Now let me pause here just a little bit. Let's go back to our diagram here. Usually when we have an ascending backfill, it's a lot more economical to have a shorter heel and a longer toe. That's because we don't want the brunt of the backfill earth pressure and any surcharges and lateral loads come in to affect the heel shear and heel moment. So that's why we made. You can obviously make it longer, but if you make it longer also, you're removing more excavation, so it will be more costly. So it's in general, if you have an ascending backfill or you have a taller wall, 10 foot or higher, it's a lot easier, more economical for excavation point of view and from design rebar point of view to go with a shorter heel. Okay, now if we had a restraint, we would click on this, and if you go into the diagram, you'll see that you have a sliding restraint. And if you go, let's close that, and if you go into the retaining wall stability, it will not compute the sliding factor of safety because you have a restraint, but it will tell you what restraint you need. In order to get 1.10 factor of safety for sliding, because we have seismic earth pressure, you need 5669 pounds. So let's take that out. Surcharge loads. These could be strip load, where you have a rectangular load. It's a finite width and it's parallel to the retaining wall stem. X1 is the setback distance to the beginning, and X2 is the total distance from the back face of the upper stem to the end of the strip load. We can also have a line load surcharge, and we just need 1x, that will be in kips per foot. And we could have a point load surcharge, which is just a kip, and it's a similar notation as a line load. In this case, we don't have it. We don't have any surcharges. Additional lateral loads. We spent a lot of time making this, about approximately 8 months, going from version 2 to version 3. And the reason is we found that when you design retaining walls, you could have all kinds of additional lateral loads. So in this case, we named one car impact load, another one is slope creep, which is possible in descending slopes, certain soils. We also have expansive soils thrust. You could have guardrail load. If you wanted compaction, you can say I have a compaction load. And then if you wanted additional, let's say you have impact load of some sort, say impact load, you could do that. And if you didn't have, well, we actually have impact load. So let's say we have something due to temperature. Okay, you could have that, and then you'll enter, for example, it's 4.5 feet from the top of the stem, and it happens to be 2 kips. That's how you'd enter it. In this case, we don't have it, so let's take it out. But what I wanted to say is you don't have to have the name car impact load. If you want this to be your slope creep, you can say this is a slope creep. Okay, and then you can call it whatever you want. And then you'd enter, again, it's 4.5 feet, and slope creep is normally about 1 kip per foot. And then if you have 0 anywhere else, then obviously there will not be any calculations. So that's what you do. If you had 2, you'd go to the next one and say, okay, this is my guardrail load, and then you could say, for example, this is 0.3. It's half a foot from the top of the stem, and it's half a kip, for example. Okay. So that's how you use these additional lateral loads. Let's take them out since we didn't have any. So that's 0, and that's 0. Okay, now we also have factored moment, but pay attention that it is factored. It's already with the 1.6 multiplied. So if you had, let's say, moment 1 coming from some equipment, then you'll say, okay, from the upper wall, from the top of the stem, it's 3 feet down, and it happens to be 5.5 kip foot or foot kips. And when you go into the construction, you will see that it's 5.5 kips at 3 feet from the top of the stem. But we don't have that, so we can take it out. So as you can see, you have a lot of room to add any kinds of loadings that you can imagine. Okay, the next is use base shear keyway. If you go back to the diagram, you can see the shear keyway. We can take that out. So if we say we don't need that, you go in and the shear keyway disappears. The only problem is now your sliding factor of safety is less than 1.10 when you have seismic earth pressure. So let's go back and put it in, and it came back to 1.1. Obviously you can have it higher, but that's where we like it, 1.1 or more. Okay, now there is something in the IBC section 1807.2.1 we're asked to consider if there is earth pressure on the keyway. In my opinion, there is really no way to justify active earth pressure on a keyway. The keyway just has a resistance passive. So the code doesn't stipulate that we have to use it. It says that you have to consider, but there are some municipalities that always, they always request that it should be done. Now, there are two thoughts that come to mind. Does the opposing keyway pressure start all the way from the top of the stem, and instead of ending the earth pressure at the bottom of the footing, does it continue all the way down, or does it start at the top of the keyway or the bottom of the footing? Well, in our opinion, you really don't have that, but if somebody was to insist on it, because you have a heel, the earth pressure is being interrupted. You have a jog, which is 2.17 feet, and then you have a keyway. So if you have your keyway 3 foot is more than the jog 2.17 feet, then obviously you cannot continue the earth pressure from the top of the stem. So it would come from the top of the stem to the bottom of the footing, and then you'll start 0 again, and then go at 40 psf per foot for active. And if you had at rest, if this was a basement wall, restrained wall, then you'd go say 60. But you cannot have additional loads because, for one thing, it's below the point where you do the overturning and the sliding, which is right here. So anyway, that's how you'd use it. So if you had that pressure, 1807.2.1, you'll say apply the pressure. Okay, and now look at what happened to your sliding factor of safety. It went from 1.10 to 1.06. Okay, and then we like to reinforce the keyway, and in this case we use number 5 at 16. Then we have heel reinforcement. We had number 5 at 8. So every time you do something, you check. So for example, let's go back to base shear keyway, and then you go here and say base shear keyway. You can see that everything is green. Okay, if you wanted number 5 at 18, you can do that. But we cannot go, if you said number 5 at 21, the program will default back to 18. For ACI code, you cannot have reinforcement spaced greater than 18 inches on center. So let's go back and keep it at number 5 at 16. Because it's touching soil, the bar cover is minimum 3 inches. Now we're doing heel reinforcement, so we can go to heel reinforcement, and you could see that if, let's say, why we don't want to use number 5 at 8, let's try number 4 at 8, and it's still working. So if we said, well, let's try number 4 at 16, then you find out that you have a red here. The reason is the actual row is 0.009, and row minimum is 0.0018. And so let's go back at number 5 at 8. The other reason why we chose number 5 at 8 is if you look at the bottom, let's go to the reinforcement. If you look at the number 5 at 8, and we're getting that into the footing, sometimes we like to bring this all the way down and then match the toe bars. That's why we said number 5 or 8. But if you wanted to match every other one, obviously you could say, you could go back sort of to the toe and say it's number 5 at 16. And that would be fine. But now when you go to toe and check it, you have an issue. So that's why we like to say keep it at number 5 or 8. Okay, then shrinkage and temperature. So if you look into the reinforcement diagram, these are your shrinkage and temperatures. Okay, and then here at the top. So the beauty about this version is you can say calculate, and there it gives you the maximum spacing, but it will not exceed 18 inches. So if you look at it, the program here says the number of bars at the bottom is 5. So on the bottom of the footing, 1, 2, 3, 4, 5. And then it says number of bars at the top on the heel is 4. So 1, 2, 3, 4. You don't need any temperature and shrinkage here. This is not intention. And this one is already developed. And then it says number of bars for the key is 3. So that's 1, 2, and 3. Okay. And then the last but not the least is the footing settlement. You add the Poisson's ratio. You have the elastic soil modulus. So if you did not know that, you could say, well, I have medium. In this case, we said we have something that's silty, slightly clay. So if you say 700,000 to 800,000, 700, that's 800. This one begins at 700. That's about right. So we left that at 7. If you were, wanted to be in the middle between 700 and 900, you can go 800. This is the vertical subgrade modulus, just like when you design mats and combined footings. And these are the ranges, and the units are tons per cubic feet. Okay, so to check that, the footing settlement, you'd go over here and see that the settlement is less than 1 inch. Obviously, if it's more than 1 inch, then you have to come back into your construction diagram and then say, well, wait a minute, I need a higher bearing capacity. Maybe check with the soils engineer because the footing width is wider than 2 feet or 2.5 foot. Maybe there is room for that. Or you'll have to go ahead and change the surroundings, the bottom soils, and replace it with rock or something similar to that. If neither of these options are available, then you have to increase the footing width until you meet the allowable bearing capacity and settlement. So the program checks that you have both. Okay, and then here is the reinforcement. And then when you say file, you can say print, and then you can say preview, and it takes about 3-4 seconds to the database to collect everything, make the print file, and then when it's ready, it will let you know that you can open the file and take a look at it. And there it is. That's on sheet 1. Now, one other thing that we added on this version 3, if you go and highlight, if you zoom into it, we wanted to make sure that you consider the material aspects of the retaining wall design. So per ACI 3.18.14, table 19.2.1.1, you have to follow the compressive strength requirements. The other table, 19.3.1, it's exposure categories and classes, and 19.3.2 is the mixture requirements. So you can look at the second page, third page, and so on, all the way to the end. And if any of you want to get more retaining wall textbooks and references, here are the 14 that we used. So now you can say print, okay, and you can print into a PDF or click here setup, and then you can choose. So if you had an Epson or whatever other you had, if you wanted to fax it, you can go straight to fax. If you want, let's see, PDF 995, whichever program you have. So if you said this, then you could say OK, and then it will print. So in this case, let's cancel it. And then you can go back, you can close this, and it will go back into your program. And then the final thing I wanted to mention is we spent a lot of time making sure that you develop all the bars correctly. So in this case, you could see you need 20.1 inches to develop these number 5 at 16 bars onto the middle stem, and then you need 16.4 from the middle stem to be developed into the bottom stem, and you need 9.6 inch hook depth. And this is calculated. You could see the distance from the back face of the stem into the end of the heel bodies is 21.4, and for the toe bodies to be developed it's 16.4. That's from here to the end over there, and you've got the temperature and shrinkage, so it's all ready to go. We thank you for your time and hope to see you in the next video.